Welcome to the Explainer. All right, let's just dive right into this ultimate exam review masterclass. We're going to demystify the core foundations of computer hardware and software today. Whether you're a complete beginner who's just trying to figure out how your laptop actually works, or you're laying the groundwork for a future career in IT and system administration, this foundational knowledge is exactly what you need. We're going to decode the complex language of computing into simple, easy-to-grasp concepts.
This study guide is going to be our roadmap today. We'll cover 1. The evolution of computing, 2. Anatomy of a computer, 3. Understanding computer memory, 4. The flow of data, 5. Software, system versus application, and 6. Data security and recovery.
So let's start with Section 1, the evolution of computing, from mechanics to microchips.
You know, the devices we use today didn't just appear out of nowhere. They're the result of centuries of compounding innovations. It's really a story of physical circuitry transitions. We shift all the way from mechanical, hand-operated devices like the abacus way back in 500 BC to Charles Babbage's analytical engine in the 1800s, which actually laid the conceptual groundwork for inputting, processing, and storing data. And then we hit the electronic era. The ENIAC in 1945 was massive. It relied on bulky, incredibly heat-generating vacuum tubes. But the real game changer? That was the invention of the transistor in 1947, which replaced those giant tubes with tiny semiconductor materials. By 1970, we were packing entire processing units onto tiny integrated circuits, giving birth to the modern microprocessor.
That microchip revolution leads us directly to a pretty famous observation. Back in 1965, Intel co-founder Gordon Moore famously predicted that the number of transistors on a microchip would double every 2 years. This completely explains the exponential growth of processing power we've seen over the decades. It's exactly why computing evolved from those giant machines that took up entire rooms all the way down to powerful personal computers, wearable smartwatches, and the interconnected smart appliances we use today.
Moving on to Section 2, anatomy of a computer, the physical components.
If you're aiming for a role like a hardware technician or a system administrator, understanding these core physical components is your absolute baseline. At the center of it all is the Central Processing Unit, or CPU. Think of the CPU as the brain of the computer, but we can actually divide this brain into specific lobes. It utilizes the Arithmetic Logic Unit, or ALU, to act as a high-speed calculator, crunching all the math and logic operations. Meanwhile, the Control Unit acts like a highly efficient traffic cop. It controls the sequence of instructions, interprets them, and directs all the communication and data flow between the other components of the system.
Now, to interact with that brain, we need peripherals. You can cleanly divide these into input devices, which send control signals and data into the computer, versus output devices that produce human-understandable results out of the computer. Things like keyboards, mice, and even your voice sending signals to a smart assistant, those are inputs. On the flip side, your monitor, speakers, and even modern 3D printers building physical prototypes are all output devices.
All right, Section 3, understanding computer memory, storage scales.
Processing is utterly useless if the computer can't remember what it's working on, right? At the absolute foundation, and this is great if you're a complete beginner, a computer only understands two states, on or off. We call these tiny units bits, represented as a 0 or a 1. Basically, think of it like a single light switch. Group 8 of these light switches together and you get a byte. From there, memory scales up massively. Kilobytes, megabytes, gigabytes, which you're probably super familiar with on your phone, all the way up to massive yottabytes, which represent the unimaginable scale of data managed by huge enterprise data servers today.
When it comes to where data actually sits during operation, the most heavily tested concept is primary memory. We have two main players here. RAM, or random access memory, is your volatile temporary desktop workspace. It holds whatever you're working on right now, but if the power goes out, the disk gets wiped clean. ROM, or read-only memory, is completely different. It's a non-volatile, permanent storage space strictly meant for crucial startup instructions, like the bootloader that wakes the computer up in the morning.
Building on that, we also have to contrast this primary memory with secondary memory. If RAM is your temporary desktop workspace, secondary memory is your permanent filing cabinet. It holds your data, your photos, documents, and installed programs, even when the power is completely shut off. Secondary memory includes things like traditional hard disk drives or much faster solid-state drives. It's a bit slower for the CPU to access than primary memory, but it holds vastly more information.
Section 4, the flow of data, tracing the journey.
So how do all these parts actually talk to each other? Let's diagram the flow of signals and track a single keystroke.
When you press a key on your keyboard, an input signal is sent and temporarily stored in the primary memory, the RAM. From there, the CPU's control unit steps in. It directs that piece of data over to the arithmetic logic unit for any required processing. Once the ALU does its job, the control unit routes the final process data out, either displaying it on your monitor as an output or saving it down into your secondary storage filing cabinet.
There's one brilliant little trick the computer uses here, though. Because the modern CPU is incredibly fast, often way faster than the RAM, a high-speed cache memory sits right between the two. The cache stores copies of the most frequently accessed data. It acts as a super-fast buffer to supply the CPU with exactly what it needs instantly, preventing system bottlenecks and keeping everything running buttery smooth.
Okay, Section 5, Software, System versus Application.
Hardware is literally just an expensive paperweight without instructions. So let's explore the invisible half of the computer, software. The absolute most critical piece of software on any machine is the operating system, like Windows, Mac OS, or Ubuntu. The OS is essential because it interacts directly with the hardware at a fundamental level. You honestly cannot use a computer without it. It allocates memory, manages the CPU, provides security, and creates a stable platform so that you, the user, can actually interact with the machine.
And because we're constantly plugging in new hardware, like a brand new printer or a specialized 3D mouse, the operating system needs a little help understanding them. To manage these new devices, we use device drivers. These act exactly like language translators. They bridge the communication gap, hiding the complex hardware operations and helping the operating system communicate seamlessly with the new peripheral.
Once the system software is up and running, we use application software to actually do our work or just have fun. When looking at application software, it's vital to note the difference in how they're distributed. Proprietary software, like Microsoft Windows or Adobe Photoshop, is software you have to purchase from a vendor who holds the copyright. Freeware, like Skype, is software you can use at no cost, but you can't peek under the hood to see how it's built. And then there's free and open source software, or FOSS, like Ubuntu or Python, where the code itself is freely accessible for anyone to modify, improve, and share with the world.
Finally, Section 6, Data Security and Recovery, Real-World Implications.
If you're stepping into a professional system support role, this right here is where theory meets high-stakes reality. It brings up a trap so many people fall into. When you hit delete on a file and you empty that recycling bin on your hard drive, is that data actually erased?
Surprisingly, no way. Deleting a file just marks its address entry as free space. Think of it like ripping the chapter title out of a book's table of contents. The actual pages of that chapter are still sitting right there in the book. This means the raw data stays perfectly intact on the drive until new information eventually gets saved over it and overwrites it.
So the absolutely crucial point here is the massive security risk of just tossing out old, non-functional storage devices without properly shredding or wiping the data first. Because the data isn't truly gone, anyone with some basic data recovery tools can retrieve your deleted files, your passwords, or your personal documents. It forces us to ask a rather uncomfortable question as we wrap up. What incredibly sensitive data might you be unknowingly throwing away in the trash today?